So hey everyone, the Maths and Physics Club is excited to introduce you to another talk in the series of online Quarantalks. Our speaker for today is Arkya Chatterjee, a first-year PhD student at MIT who graduated recently from IIT Bombay. He's an amiable person and shares a passion for physics and will introduce us to the quantum realm of the Hall effect. Before we start, I request everyone to turn off their webcams and microphones. We will be taking questions through the chat box. And thank you for tuning in. Over to you, Arkya.
Okay, great. Yeah, thanks for joining, everyone. I hope I'm audible and my screen is visible to everyone. If not, please just write in the chat. Right, I want to thank MnP Club for inviting me to speak as part of this series of talks. And I think this is a really nice initiative, and I hope it helps all of you stay connected to interesting math and science during these times of anxiety. First of all, maybe let me tell you why I decided to talk about the quantum Hall effect. I'm assuming the audience is by now familiar with quantum mechanics from PH 107. The way quantum mechanics is usually introduced, it might seem like it's a very microscopic theory, that it's only talking about single electrons or single atoms. It's not intentional, but like that's how the way quantum mechanics first was discovered. But there are a lot of macroscopic or by macroscopic I mean things that are large enough to be seen by naked eyes or by experimental apparatus. Even at the macroscopic scales, there are lots of interesting quantum mechanical effects, and quantum Hall effect is one of these examples. And I chose this phenomenon specifically because the prerequisites are very minimal. You almost put in nothing and you get a lot out of it. So hopefully by the end of this hour, you'll see why I'm saying that. With that, let me switch to a Blackboard mode, which I'm already sharing, I guess. Right, so if you can see the screen, this picture here, this is from a paper by Van Klitzing, Dorda, and Pepper from 1980. This was the first paper that observed this quantized Hall resistance. The y-axis is a proxy for Hall resistance. So you can see these plateaus here, 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 and so on. So these are quantized values of Hall resistance. I'll tell you, I mean, hopefully all of you know what the Hall effect is, but I'll review that soon. So yeah, you'll see what I mean by the Hall resistance. Yeah, so these are the quantized values that I'm talking about. And this was the first time this was observed. And the system was a MOSFET, a P-type MOSFET. MOSFET, if you don't know what that is, it's okay. It's just a 2D system with electrons. Yeah, that's about it. This was 1980. Since then, there has been a lot of research, obviously, and this is kind of the state of the art, 2011. This is in graphene. So you might have heard of graphene. Graphene, there has been one Nobel Prize on it, and I guess a few upcoming. The graphene is this exciting material that everyone is excited about, and it's this hot topic of research. Anyway, so this graph is graphene, and this is bilayer graphene, which is two layers of graphene sandwiched together. So you can see even more pronounced sort of plateaus in the Hall resistance. The red one is the Hall resistance, and the green is something we'll talk about soon. Anyway, so yeah, this is the current state of art. The reason I say this quantum Hall, I mean, the quantization of Hall conductance was surprising, was because the kind of, I mean, for comparison, the kind of quantization people had seen till then was, let's say, in this superconductor. So if you have a ring of superconductor and you pass a magnetic flux through it, it turns out that that flux is quantized, and this is the kind of quantization people observed by then. These dots are the experimental data. And you can see the dots are almost all over the place. If you compare with this graph here, these nice plateaus, I mean, this is kind of all over the place, these dots, and the lines are sort of fits from theoretical, from theory. So yeah, this was very, very surprising to see a solid state system showing such nice quantized behavior. with that, let me switch to the actual discussion. So first of all, I'll be talking about the classical Hall effect, and to tell you what it means, let me just show you the experimental system. So I hope you can see this. Yeah, so this is the Hall measurement, like the experimental apparatus for measuring Hall voltage. So you apply a magnetic field perpendicular to the system, and the system is basically like a rectangular slab with W being the width, and you pass a current this way, perpendicular to the magnetic field, and you measure the voltage mutually perpendicular to both of these across this, right? Maybe use blue. Right, so this is kind of what the Hall measurement setup is. So keep this picture in mind. This will be sort of the constant throughout this entire discussion. So yeah, let's see. Let me then write down the equations of motion. Sorry. Yeah, let me write down the equations of motion. So in the classical Hall effect, we'll be using Newton's equations, which is, as you all know, mv dot equals q. Okay. Right. So this is your Lorentz force and electric force, right? So this force is just in your classical mechanical sense, but when we talk about a solid, we usually talk about electrons as a gas moving in like a background of positive charges. And because of the positive charges, electrons collide with them and lose some energy, and that loss of energy is modeled by this term. This is known as a relaxation term. So if you incorporate this term, what you end up getting is that you have something like this. You get basically, you basically get Ohm's law. This is the conductivity. Oh, by the way, like feel free to unmute yourselves and ask questions whenever you feel like you're not following what's going on. I hope everyone's with me so far. Okay, I have no feedback here, but I'm assuming everyone's okay with this so far. Anyway, so this is the kind of equation you'll get if you rewrite this equation in terms of the current, which we write as NeV. N is the density of electrons, E is the charge of electrons. Maybe put a minus sign here because electrons are negatively charged, and V is the velocity. So if you write this equation in terms of J, you get this. Anyway, now what is the form of sigma? The inverse of sigma is rho. You can like sigma is usually a tensor or a matrix, so it's written this way. Right, and its inverse is known as the resistivity. I mean, this is something familiar to you from like JEE or undergrad first year courses. So this equation actually can be rewritten as this. So it's a matrix equation, and you have and this term might be familiar to you from PH 107. I don't know if you guys did this, but this is the resistance that you get in what is known as the Judo model. So Judo model is this old model of solids from 1900s. So according to that theory, this is the equation that you expect, where I should tell you what omega b is. Omega b is given by EB over m. M is the mass of the electron, E is the charge of the electron. So, right, so this is the kind of equation you get, and this is what I've been calling the resistivity tensor. Actually, yeah, rho should be written as. So the moral of the story is that the resistance that you observe when you apply an electric field EY, sorry, let's say. So, right, when you apply a current Jx, what is the electric field you observe in the y direction? It's given by rho yx Jx. And this EY, if you remember the diagram, so EY across this direction will lead to a voltage EY dy, right? So EY is related to the Hall voltage, related to the Hall voltage. I mean, this perpendicular voltage is what I'm calling the Hall voltage. So at the end of the day, if you evaluate this BH, you're essentially like trying to measure what rho yx is. So the rho yx you get here is B over NE. If you just work out this off diagonal term, multiply with this is what you get. Right. So why is this, I mean, interesting? This is interesting because if you plot the two resistance as function of magnetic field, so the other resistance that I've been talking about is rho XX. This is the longitudinal resistance. So if you apply, so this tells you what happens if you apply a current in the X direction, or if you apply an electric field in the X direction, what is the current in the X direction? So this is given by this. This is a different kind of experiment where you apply an electric field in this direction and you measure the current also in this direction. So this is known as the longitudinal resistance or longitudinal resistivity. So you get rho xy to be linear, or rho yx to be linear in B. Like you can see, like N and E are, these are constants. B is the variable here. So rho yx goes this way, and rho xx turns out to be just this. You can see from here. So this is the rho xx component multiplied with this quantity. You get this. So this is a constant because m, n, e squared tau are all constants of the material. So this remains like this. So this is the expectation from classical Hall effect. You don't see any plateaus in this. In the rho yx, you don't see any plateaus like you were seeing in the graph before, right? So we need to figure out where these plateaus come from. And the first step towards that is trying to understand the quantum harmonic oscillator. So let me switch gears here a little bit. And okay, there are chats. Okay, never mind. Yeah, I can't see any ways to like do a poll, but is everyone familiar with quantum harmonic oscillator? I guess not. So I'm gonna review that quickly. Okay. Can you raise your hand if you've not seen any quantum mechanics before? Okay, no hands. Okay, great. So I can directly go to the quantum harmonic oscillator. Right. So the Hamiltonian for a quantum harmonic oscillator is given by this. So omega is the frequency of the oscillator, P is the momentum operator, X is the position operator. Right. So to diagonalize this Hamiltonian or to find the energy spectrum, it's convenient to introduce some operators or some new operators, which are these. and A dagger, which is the harmonic conjugate, which is the complex conjugate of this, or Hermitian conjugate of this, which is right. So in terms of these new operators, it's possible to show that this Hamiltonian reduces to a simple form. Now, why is it simple? It's simple because these A and A dagger operators actually describe a discrete spectrum of states which are characterized by this n, and n belongs to well, n union 0, the positive non-negative integers. Right. So A and A dagger also have this nice commutation relation. If you know that XP have this commutation relation, you can work out that A and A dagger will have this commutation relation. And as a consequence of this commutation relation, one can show that these states have a nice property where A dagger raises the number here. A dagger gives you, forget about this normalization, it's some normalization constant, but it sends you from n to n plus 1, and A brings you from n to n minus 1. So essentially you have like this ladder of states separated in energy. So the energy, I should tell you, the energy corresponding to this is En h bar omega n plus half. Right, and the separation, so you can see that like the energy levels are separated by energy h bar omega. So operator A takes you from the nth state to n minus 1. This is A, and A dagger takes you one level up. Right, so this is why we call A dagger as a creation operator. It's as if creating one new, it's increasing the number, and A is known as the annulation operator. And together we call these ladder operators. Right, and there is one state, 0, which is annihilated by A, which means this becomes like identically 0. So this is known as the vacuum state. And so this can be this. So this translates to a differential equation. Let's call the corresponding eigenfunction as psi 0. And there is some differential operator which this translates to, and you can solve this differential equation. You get some form for psi 0. Then you act with A daggers n times to get psi n. And this psi n of x is given by this nice formula, which you can see on Wikipedia. So Hn is what is known as a Hermite polynomial. It's a well-documented a mathematical function. And this is the Gaussian form that you have. So in general, like the 0th level for n equals 0 looks like a Gaussian, and the higher levels all look like kind of modifications of this, like modifications by Hn. So yeah, this is kind of a brief overview of the harmonic oscillator. I'll tell you why we need this, but first let's also review some electromagnetism. So you might remember from EM course that magnetic field is given by this formula where A is the vector potential. If we use this in what is known as Faraday's law, it turns out that E plus del A del T has to be some gradient, right? If you just substitute this here, you end up getting this. Now, it turns out that if you add some function, some gradient function to A, it doesn't affect B because the curl of a gradient is 0. So if you add some gradient function to this, and at the same time, if you subtract the time derivative of that function, this ends up leaving E and B fixed. So this is what is known as a gauge transformation. and we'll be using this fact later. What this means is that A and phi can have like this redundant degrees of freedom, which you can like fiddle with and leave your physical degrees of freedom, which is E and B, fixed. So we'll be talking about something known as a Landau gauge in this talk. So keep this in mind. So gauge just means a choice for your for the form of your vector potential. We'll be ignoring this phi here mostly because we'll be talking about the magnetic field usually. So right, so the Landau gauge is given by you only have a component in y direction. You can quickly check that this gives you a constant magnetic field in z direction. So yeah, like I said, we'll be considering a constant magnetic field in the z direction. So you can see that del cross A gives you this turns out to give you B z cap as we want. So yeah, just keep this in mind. There's another gauge. There's another important gauge that we'll talk about, which is symmetric gauge. This is nothing but so yeah. In all of this, B is constant and in the z direction. So keep these two things in mind. Yeah, let me stop here and see if there are any questions, because next we'll talk about Landau levels. If anyone has any questions, please unmute yourself and ask. Okay. Great. I think there are no questions. So let me now talk about Landau levels. So the Hamiltonian for an electron in a magnetic field is given by this. If I had more time, I would have probably derived this for you, but just take it from me on faith for now. So for any charged particle, actually, like the Hamiltonian is given by this. And since Q is minus E, you get this for an electron. So to diagonalize this Hamiltonian again, we need to define this as a canonical momentum. And using the commutation relation of x and p, we can show that the components of this, pi x and pi y, in all of this, all of our variables will be 2D. Like momentum is given by px, py, because there's no dynamics in the third direction. It's all in 2D. Okay, yeah. So pi x and pi y have this commutation relation. Now, this might remind you of the kind of commutation relations we saw earlier. Like this might remind you of xp equals ih bar. If that reminds you of xp equals ih bar, then that's great, because that's kind of the intuition we use to define the new creation annulation operators, the ladder operators. So we use this to define this and a dagger, which is the dagger or the Hermitian conjugate of this operator, the other operator. So yeah, a dagger accordingly. So it turns out that these ladder operators also have the commutation relation we had earlier, which is nice because this kind of tells us that the spectrum is identical to what we had. So we again end up having these evenly separated energy levels with separation energy given by h bar omega b. Omega b, as I told you earlier, is EB over m. And yeah, so this is nice because we used our known result from the harmonic oscillator. Again, the energy levels are characterized by this integer n. and En is given by. Now what we'll do is we'll choose the Landau gauge, which is nothing, which makes the Hamiltonian slightly simple. Remember that the Landau gauge had Ax equals 0 and Ay equals Ebx. So you only see a term of Ay in the y part, right? So the reason we're doing this is we want to see what the wave functions look like in real space. And it turns out that since this Hamiltonian commutes with Py, you can check that because there's no y appearing here. So everything here commutes with Py. Only y doesn't like commute with Py. So since y doesn't appear here in the Landau gauge, this is 0. So we can write our wave functions in this form, where the y part just comes as a plane wave, and you have these this other part, which is only dependent on x. So if you, this is what is known as an ansatz. So if you substitute this ansatz, you end up getting these nice looking Landau levels, which I'll show you. Let's see. So this is, so this is the lowest Landau level, n equals 0. And this is the second Landau level. As you can see, like in the x direction, they have these nice Gaussian profiles, as you would expect. And in the y direction, we had, in the y direction, they have this nice sinusoidal behavior where they just oscillate in the y direction. And in the x direction, they have this localized Gaussian profiles that comes from the harmonic oscillator kind of discussion. Okay, so again, this just confirms our algebraic analysis, which said that we should have energy levels similar to the harmonic oscillator. But these levels, these Landau levels, are highly degenerate. So to discuss this degeneracy, we first need to impose a hard boundary condition in the x direction. So let's say the wave function can only exist between 0 and Lx, right? And so if you look at this, these functions here, these have like centers, Gaussians centered at various locations. This location can be written in terms of the k variable. I didn't show you the derivation, but let's say you can work that out. Then the centers, these centers are given by minus k lb square, where lb is a magnetic length, which I define as, let me check my definition. So lb square is given by h bar over eb. I mean, this is not very hard. This is just algebra, which you can work out simply by substituting this ansatz in this equation, right? So you get a harmonic oscillator equation, which has a shifted origin, and this is the origin. So this center KLB square minus KLB square must lie between these two limits, right? Because we have a hard boundary at 0 and Lx. So what this condition tells you is that K must range from minus Lx LB square to 0. At the same time, if we impose a periodic boundary condition in the y direction, you'll get discretized values of K. This must be something you've seen in PH 107, and the discretization turns out to be of this form. So this is the kind of discrete set of K values that are allowed. So we ask ourselves, how many such discrete values are available in this range? That value turns out to be equal to this, and this is nothing but E times flux over H. So flux is given by B times Lx times Ly, as you know. Or this can be rewritten as phi over phi naught. And this phi naught is something that will, right, seems to be working. Okay. Oh, okay, sorry about that. Right, yeah, okay, where were we? So the dispersion, so this is what is known as a dispersion relation. And when we take this derivative, we get the velocity. So yeah, okay, so why is this velocity important? Right, so let's see. So first of all, when we fill up the levels, as you saw, the Landau levels were sort of like localized around these x values. So when we fill up these levels, they look like this. Let's see. So these are the filled states here. If you have some chemical potential or some Fermi energy, which lies around here, you fill up all the levels below that. And since we saw that the Landau levels in the Landau gauge, they are sort of localized in the x direction as Gaussians like this. So filling them up kind of looks like what is shown in this diagram, right? So here you see some slope in the dispersion relation, or this is actually the potential. So let me actually switch to, okay. Right, so filling up Landau levels looks like this, right? You also fill up here, 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 and so on. Now, when you apply some potential difference across the sample, like so this is, let's say this is 0 and this is Lx. So when you apply a potential difference across that, what you end up doing in Whittaker's theory is that you end up tilting your energy dispersion. So, or actually, let me take this interpretation first. What you end up doing is you apply different chemical potentials. So this is, let's say, EFR, this is EFL, right? This difference is the potential difference you're applying, right? And this leads to a current. Why? Because if you integrate this value of current here, so let me just finish this expression here. This is E, this turns out to be equal to E over B. And if you remember this connection here, so here we chose our electric field value. If we correctly choose capital E, we should be making this kind of a mapping. So if we rewrite in terms of this, you actually end up getting this. So now in this part of the wall, the derivative is positive, right? And here it's negative. So what this does is this causes the velocity here to be positive, or actually the other way around, because there's a negative sign here. The velocity in this part of the wall, sorry for making this so ugly. Yeah, so the velocity in this part of the wall, the velocity in the y direction is negative, while the velocity in this part of the wall is positive. And this is precisely what the Hall current is, right? You apply a potential difference in the x direction, it causes the Fermi levels to like have a relative separation. And as a result, you see that the currents in the two edges flow in the opposite direction. So this is what is known as chiral transport. So that's because, like, on the right hand side, the velocity is only negative, while in the left hand side, the velocity is only positive. So there's a sign that's fixed by the physics. So that's known as chiral modes. And these edge modes are responsible for the Hall current in the quantum mechanical picture. So if we want to calculate the total current, we need to integrate over all the modes or all the k values, and the current will be given by This is the velocity, this is the density of electrons, and this is an integration over the K space. So you end up getting a current. So this is the current density. This is current density. So if you write the current as JYLX, that turns out to be equal to VH is nothing but the difference in the Fermi levels in the on the two sides. This gives you a first hint as to why the current or why the conductivity is quantized. So if you see, this is precisely the constant that I was talking about in the abstract or earlier. So this comes from a single Landau level. If you have new Landau levels filled, so that will look like, let's see if I have the picture. Okay, I don't have the picture, but if you have new Landau levels filled, you just have nu times this current, which is nu E square over H times VH. And since IY is related by sigma YX VX, so this is nothing but sigma YX, or the Hall conductivity. So this gives you a first signature of why the Hall conductance is quantized. It's quantized in multiples of E square over H. Looking at the time, I guess I might have to skip through a lot of important stuff. I wanted to talk about gauge invariance as well as topology, but maybe I need to skip the gauge invariance part. Let's see. So maybe, yeah, let me first talk about spectral flow. Right, before going there, does anyone have questions? Can you put the flux quantum in quantum Hall conductance? Anirban, can you explain that question? Okay. So I'm assuming you mean like, so this is exactly the Hall conductance, like sigma YX here. This is the Hall conductance. So this has to be some integer, like nu is some integer in this set. Nu tells you how many Landau levels are filled. So the plateaus that you saw in the Hall conductance graph that I showed you earlier, those plateaus tell you how many Landau levels are filled. Okay, I hope that answers the question. How good is the approximation of non-interacting? Right, so all of this is assuming electrons don't interact with each other. And this is good enough in some range of magnetic fields. It turns out that if you increase the magnetic field to much higher values, you have what is known as the fractional quantum Hall effect, where you have to take into account electron-electron interactions. But for now, we're using non-interacting electrons, so there's no dressing up of the mass of electron. Does that answer the question, Guru? Okay, thanks. Okay. Okay. Any other questions? What happens in graphene? Graphene is just, it just so happens that in graphene, it's easier to make the sample clean. Okay, I should, yeah, it just means that it's easier to avoid disorder in graphene. I am not an expert on graphene in any way. So, I mean, all I'm saying is very qualitative. But yeah, it just so happens that it's easy to make the sample clean in graphene. And that just makes the plateaus more pronounced. And yeah, even at room temperature, you can have, you can see these quantum Hall plateaus. Also, graphene has high mobility, so that helps. That helps a lot. Okay, any more questions? Okay, that seems like there are none. Okay, so this finishes the first part. I was planning to have like 3 parts of this talk, but the first part took like 45 minutes. So I'm definitely gonna have to breeze through the rest. Let me talk about one of the most interesting interpretations of the quantum Hall result. This was due to Robert Laughlin. So what he did was, instead of considering a rectangular system, he considered a ring and a flux through that ring. So let me try to draw this. So there's some flux through this. And instead of considering a rectangular sample, what he did was he just connected these two ends and turned it into a ring. So his argument was that if Hall conductance was supposed to be quantized, it should be quantized in whatever geometry you choose. So it should be quantized even in this geometry. So here you simulate the electric field by changing the flux. From Faraday's law, electric field is given by this, the rate of change of flux. And if we change the flux slowly, so at t equals 0, let's say you have 0 flux. And at t equals some capital T, let's say you include 1 flux quantum. This would lead to an electric field of minus phi naught over T. And if during this time, n electrons were transported from the inner edge to the outer edge, then the current perpendicular, the current in the, okay, I should probably also tell you that there's a magnetic field through this as usual, right? Like you have a magnetic field through the system, but you also have this added flux. Okay, yeah, sorry, I missed that. Okay, so the electric field that's generated in the azimuthal direction or the angular direction, this is the EMF, right, from Faraday's law. This leads to a current in the radial direction, which is minus n times E over T if n electrons are transported. So, and if you combine these two, sigma xy is I over E, and this turns out to be NE square over H. So this seems like a microscopic explanation for the Hall conductance being quantized. All we need to confirm is that indeed there are an integer number of electrons which are transported. And to understand this, actually we need to go to the symmetric gauge, and that's another longish discussion. So I'm probably gonna skip the details of the derivation. I'll just show you what the wave functions look like in the symmetric gauge. So the symmetric gauge, to remind you, looks like it has components in both x and y directions. And the wave functions, it turns out that the Landau levels have all these, Landau levels are characterized by 2 integers. N signifies the SHO index, which just means that each value of n corresponds to a different energy level. And M is the degeneracy index. As you remember, each Landau level has a large number of degenerate sublevels. So these diagrams here show you the degenerate levels within the first Landau level or the 0th Landau level. As you can see, if you increase M, so these are values of M. As you increase M, what happens is your wave functions get localized at larger and larger radius, right? That should be clear from this diagram. And right. So these radii are given by Rm equals 2m Lb square. You can find this out from just the form of their wave functions. Yeah, I'll probably not go into that. So what happens is when you change phi, when you change this phi from 0 to phi naught, an interesting behavior happens to these wave functions. Let's denote the mth degenerate sublevel within one particular Landau level as psi m. What happens is when you tune the magnetic field, psi m goes to psi m plus 1. And psi m plus 1 goes to psi m plus 1. goes to psi m plus 2. The reason this happens is because of the form of the Hamiltonian, actually. So let me just write down the Hamiltonian and not like do the full derivation. So when you have this flux, your Hamiltonian actually looks like, writing down just the angular part, neglecting the radial part. So it looks somewhat like this. And this a phi in the presence of a flux is given by phi over 2 pi r. This you might have done in electromagnetism course. Anyway, so if we put this in here, you end up getting something like, I'm skipping some steps here, obviously. You end up getting minus I del phi plus phi over phi naught whole square. So when phi is 0, you only have this term. But when phi is slowly tuned to phi naught, you have an additional term here, right? So all I'm saying here is that when you tune up phi from 0 to phi naught, the psi m level at phi equals 0 goes to psi m plus 1 at phi equals phi naught. So this psi m plus 1 is the new m plus 1th wave function when phi is phi naught. And similarly, all other levels just follow the same procedure. So if you remember the wave functions, they're localized in different radii. So let's say this is m plus 1. So m travels to, like, this is obviously angularly, I mean, imagine this to be like symmetric in the angular direction. So let me switch colors. So let's say this is Rm. So let's say this is Rm, and this other one is Rm plus 1. The wave functions flow towards higher radii simply because Rm is an increasing function of m. So what this ends up doing is, since every level just moves outward by some amount, m goes to m plus 1 goes to m plus 2. The net effect is that there's one electron being, if all of these levels are filled, the net effect is just that one electron gets transported from the innermost edge to the outermost edge. And this completes Laughlin's argument, because if you have n filled Landau levels, each of these Landau levels have these degenerate sublevels with radii increasing by this kind of a relation, and each level undergoes this. This is known as spectral flow. Each level undergoes this spectral flow, and as a result, you have n electrons being transported from the inner edge to the outer edge, and this completes this argument. So this tells you another way of looking at it. This actually has to do with gauge invariance, because let me probably tell you what gauge transformations look like in quantum mechanics. As you might remember, we said that the electric field is changed by this. The vector potential is changed this way, and this is a gauge transformation, right? At the same time, psi goes to e raised to minus IE alpha. Psi, this is the gauge transformation in quantum mechanics, or of the wave function. And you can see here that the derivative will just pull down this extra alpha, and that mixes with this part. So, I mean, this is very hand wavy, but at the end of the day, what happens is, at the end of the day, what happens is, when you turn on phi, you're essentially doing kind of a gauge transformation from like a gauge with 0. Well, I mean, phi is a physical quantity. Yeah, I guess. Let me rephrase that. So when I'm saying psi m changes to psi m plus 1, I'm actually doing some gauge transformation in the background, which I'm not telling you about, but that's how like gauge invariance actually plays into this phenomenon. I'm happy to like discuss this in more detail if people are interested, but it'll take significantly more time. So let's maybe skip that for now because I want to talk about the topological aspect. Okay, let me quickly stop for questions then, because I'm going to switch gears here a little bit. Any questions? You can write in the chat or unmute yourself and ask. Okay, great. Let's next talk about okay, how much time do I have? Who was the person? Sangram, how much time do I have? Hello. Is someone here?
There's no time limit. You can go as long as your lecture.
Okay, I think I might need like 10-15 more minutes. If that's okay. Okay. Yeah, I'm sorry for going over time. Like,
there's no overtime. This is just a topic.
Okay, great. Let me first talk about Berry phase. Okay. So Berry phase is a much older problem than quantum Hall effect. Starting in the 50s, people had been talking about this in various different contexts. But Michael Berry generalized these different sort of different theories into one general framework, which we now understand as Berry phase. This was done in his 1984 paper. So what we do is we consider a Hamiltonian, which depends on some parameters lambda I. It also obviously depends on R, P, and so on, like position and momentum variables. So these are some extra variables which we're calling parameters. What these parameters could look like is like external flux that we talked about just now, or some magnetic field, external magnetic field, which we can tune externally. So the problem of Berry phase is to talk about what happens if you tune these external parameters and if you make a cyclic path in the parameter space. What happens to the wave function, right? So to understand that, what we'll do is use what is known as the Adiabatic Principle. The Adiabatic Principle essentially amounts to a system not getting excited to any other state, any higher state or any lower state, as the parameter is slowly tuned in a cyclic path in the parameter space. So I'll denote like the parameters together as lambda. So lambda goes in a cyclic path. It starts at time 0, and then in time capital T, it comes back to its original values. Now let's see how the wave function changes. So as we said, the Adiabatic Principle tells us that the wave function can't be excited to any higher or lower energy states. All it can do is gain some phase, and this phase is usually unimportant. But it turns out that you can do experiments to interfere two different pathways, one which gets this extra phase, one which doesn't get it, and you can measure this phase, this relative phase between these two pathways. So it turns out that this phase is actually physically measurable. To translate this into mathematics, I will write down the Schrodinger equation. This way, right? So psi just denotes the wave function, or in the Dirac notation, the ket at time t. Now, at every value, at every point in time, let's interpret t as a time. At every point in time, the wave function, the energy spectrum. So let's say this is the energy spectrum. At every point in time, lambda changes. So the energy levels, let's say they start out in this weird form. Let me just consider 3. And they just change in some weird way slowly. notice that I'm not letting them cross. So that's one of the assumptions of adiabatic theorem. Like the energy levels can't cross as the parameters are changed. So at every parameter value, there's some spectrum of energies. Let me denote those energy eigenstates as n of lambda of t. This is a very basic notation. So h of lambda of t acting on this eigenstate gives you E of n of lambda of t. Okay, so n just denotes your different eigenstates, right? So let's say we start out in the ground state, which is this. Because of the adiabatic theorem, we'll just stay in the ground state. But the ground state wave function will obviously get a dynamical phase from this Schrodinger equation, right? If you remember, like eigenstates always evolve like some e raised to I omega n, e raised to I omega n times n. Sorry, t. Yeah, eigenstates evolve in this way from basic quantum mechanics. So this is what is known as the dynamical phase. But the idea here is that you'll get some extra phase. You might or might not, which is what we're calculating. So this extra phase is what we're calling Berry phase. So if you substitute, just a sec. So the wave function or the ket at any time t will be this extra phase, which we're calling e raised to I gamma t. This extra phase times what we expect from just simple Schrodinger evolution, which is some dynamical phase, 0 to t, e of t prime dt prime. It depends on n, of course. This is what we're after here, okay? So if we substitute this expression back in the Schrodinger equation, it turns out that we can show that at time capital T, right? At time capital T, which signifies when our circular path or the cyclic path ends, this term is given by and this is what is known as Berry connection. This is not vector potential. I'm writing A in some script notation. Okay, let me. So AI is given by the ith. We take a derivative with respect to the ith parameter of this n. Of course, n depends on lambda, right? So we can take a derivative of this with respect to any of these parameters. So the ith Berry connection is given by this expression, and if you integrate it in this is a loop integral. So if you integrate it around the loop, that gives you the Berry phase. And this can be rewritten in terms of what is known as a Berry curvature. If you take the curl of of AI in this way, again, this is a definition. So this is known as a Berry curvature. Where topology comes in is in this fact that if you integrate this curvature over a surface, over a closed surface, so this is a surface integral. So if you do this integral, you end up getting 2 pi times some integer, which is known as, the C is known as Chern number. And this is a topological invariant associated with the given manifold of parameters. So the lambda i's are the parameters of your system. So that will change depending on what your system is and what the physics is. And the space in which that parameter lives is what I'm calling a manifold. C is a topological invariant of that manifold, of the manifold of parameters. Right. So this is a first indication of how topology like shows up in quantum mechanics. Now we want to relate this to the quantum Hall physics. And for that, we need to use another piece of information from linear response theory. Okay, so quick overview of what linear response is. Let's say you have some Hamiltonian and you perturb that Hamiltonian with some added part. This added part can be, can be almost anything. It just has to satisfy the fact that this perturbation, this is what I'm calling a perturbation. This perturbation has to be small compared to your energy spectrum. So let's say your energy spectrum has this kind of a distribution. The perturbation has to be like small compared to this separation. So delta H in general has to be small compared to, let's call this delta E. Delta E. The size of the perturbation is small. And in this limit, which is known as a linear response limit, we can calculate something known as a response function. So to introduce that, in this particular case, we'll be talking about electric response, and we'll be using this relation. J is the current, A is the magnetic vector potential. In the gauge where the electrostatic potential is assumed to be 0, electric field is given by minus del T A. If you remember, I wrote earlier E plus del T A equals minus grad phi. So if phi is 0, this is some gauge choice. E is nothing but minus negative of the time derivative of A. So that's how this A relates to electric field. So if you apply an electric field, you're essentially applying some external vector potential. And what that does is it produces a response in the current, right? I mean, if you apply a voltage, you get a current. That's like first, I don't know, high school physics. What happens, what linear response theory tells us is that this current is related by a linear relation. I mean, no duh. But the linear relation is in the frequency space. So I don't know if you guys are familiar with Fourier transforms, but all this means is that if you have some signal in the time domain, or if you have some variable which depends on time, you can do something like this. It gives you, it's Fourier like a partner. So here I'm talking about the Fourier partners of these all these quantities. Okay, and this is our well-known conductivity tensor. And if we take omega to 0, this is basically what Hall conductance is. Okay, so we'll be taking omega to 0, but first we need to deal with this theory with omega non-zero. So it so happens that from linear response theory, one can show that, okay, let me just call it sigma xy, right, dc. So the sigma xy dc, it turns out to be given by a nice-ish expression. So these are all matrix elements of the current operator, Jy, Jx. These are the current operators. And so this comes basically from perturbation theory. Don't worry if you've not seen perturbation theory before. This is very standard material. You can just find it anywhere almost. Just believe me that you get something like this. Those of you who know perturbation theory can work this out on their own. Anyway, so this is the form that you get for the Hall conductance in linear response theory. Now to understand how to connect this to topology, what we'll do is we'll consider a geometry similar to what we considered in Laughlin's argument. So if you remember, this was the system we considered in Laughlin's thought experiment. We'll modify this into a torus, which is this. So instead of having a flat disk or the flat annulus in the plane, we'll have a torus, and a torus has two holes which have fluxes going through. So instead of having one flux through this, we also have this another flux going through the hole of the torus. right? All this amounts to doing is when we had this rectangular system. All we are doing is we're gluing together these edges and these edges. If you use your imagination, you might be able to see that the first, so let's say I'm calling this 1. So the first step will lead to a cylinder. And if you then glue these 2 edges, you end up getting a torus. Okay, I'm reaching the bounds of my artistic capabilities. I don't know. Okay, I mean, I guess you get the point. Whatever. So you end up getting a torus. And what you do is you insert some flux in this, just like Laughlin did. You insert some flux here. And I think in my notation, or in David Tong's notation, actually, this is phi y. So we're calling phi y. And the other flux through the other hole, we're calling it phi x. Right, and if you remember, we said that A is given by phi over 2 pi r, right? In the previous simple case. Here, similarly, you end up getting, so instead of this, you get well, of course, there's a magnetic field through the system, right? So we had just like in the Laughlin argument, we had a magnetic field through the system, through the plane. That thing remained here as well as here, just is perpendicular to the torus. So that magnetic field is already there. That gives this part, and there's another part from the flux. So phi x and phi y are some like unphysical sort of phi x and phi y have no meaning in this picture, but when you turn it into a torus by applying periodic boundary conditions, these phi x and phi y are some external handles for us to tune. So we'll kind of do the same thing. We'll as before, like we'll change phi from phi x and phi y from 0 to phi naught, and see what happens to the phase. I mean, you're probably getting some glimpses of Berry phase already. Phi x and phi y will be our parameters, which we'll tune, and we'll see how what the response is, and that response function will be related to the Berry phase. Okay, this is probably vague, but let's see how that actually shows up. Okay, so remember delta H was minus J dot A, right, in our perturbation. And in terms of these phi x and phi y, this can be written as Ji phi I over Li. Now, because of this delta H, first order perturbation theory ends up giving a modified ground state. So our previous ground state was this 0 ket. Now it's 0 prime. So these two are related by this. Again, this is standard first order perturbation theory result. If you haven't seen perturbation theory before, don't worry, just take this on faith. I'm definitely sure this is correct. Now, if you assume this phi i's here, if these phi i's are assumed to be tiny, like just infinitesimal, you can interpret this result as some sort of a derivative. So this is like change in the ket 0 divided by the change in the flux. And so delta H depends on phi I. So we're just taking a derivative of that linear function, which just leaves us with a constant. So only the Ji part, Ji over Li part will remain. And now if we go back to our formula here, this formula, you see that Jy and Jx appear here, right? But using this relation, you can connect the matrix elements of Jx and Jy to phi x and phi y derivatives of the vacuum state or the ground state. So if you use this relation to use this to rewrite sigma xy, sigma xy dc, right? You get something like this. Now, this might remind you of the expressions that we got earlier when we were talking about the curvature, Berry curvature. See, you had like some j derivative of the ith component minus ith derivative of the jth component. This has exactly the same form. If you imagine this to be related to some ax, this to be some ay, then this is del ax del phi y minus del ay del phi x. So this has exactly the same form as a Berry curvature. So if we think of phi y and phi x as our parameters, where phi x belongs to 0 to phi naught, phi y belongs to 0 to phi naught, 0 to phi naught, and yeah. So I guess I probably like mentioned this briefly when we were talking about the spectral flow. What happens is the spectrum is identical at 0, phi naught, 2 phi naught, and so on. So there's a periodicity in the fluxes. So if you change flux from 0 to phi naught, the spectrum just goes back to the same spectrum. So this is another non-trivial fact which I alluded to earlier. Anyway, so this phi naught can be identified with 0. So this is actually a periodic. Both of these are periodic variables. So phi x and phi y, they also live on a torus. Okay. They also live on this torus, which I'm gonna call t phi squared. So if you change phi x and phi y on this torus in some weird way, whatever may be your path, you're essentially doing the same kind of cyclic path as we discussed in Berry phase. Okay, so you're going to get some Berry phase out of that. And this manifold t phi square has a corresponding curvature, phi xy, sorry, fxy, right? Okay, let me not go this fast. So you saw here we had ax and ay being defined. So in terms of this Berry connection, we define phi xy as right. And if you compare this relation and this relation, you end up relating sigma and f. This e square and h bar are coming from, let's see where they're coming from. Well, you have this h bar here. And well, yeah, I mean, phi already has, I guess I should change my variables here slightly. Yeah, let me first make this, okay, sorry about that. Let me change variables to theta, which are non-dimensional. So let me call phi x over phi naught as our 2 pi times phi x over phi naught as my angular variable instead of phi, okay? Phi x over phi naught has to be an integer. Sorry, phi x over phi naught lies between 0 and 1. Phi y over phi naught lies between 0 and 1. So the theta x and theta y variables lie between 0 and 2 pi. So in terms of these theta variables, we define phi x, fxy. This is just a linear rescaling, so it shouldn't matter, but I'm doing this for consistency with my notes. Right. And if we define AI of theta as minus A0 del theta I instead of phi I, using these two definitions, what you end up getting is fxy equals minus I del theta y. And this turns out sigma xy is just minus e square over h bar times this fxy. But this still doesn't tell us why sigma is like why the Hall conductance is quantized in e square over h bar, because we don't know what, I mean, fxy could depend on the flux. So what we do is we average over these fluxes. I mean, we average over the manifold T phi square, which amounts to just integrating over the theta variables. Doing an average, so you divide by 2 pi over 2 pi square. Right, okay, so this is what you get. And if you remember, we said this quantity, this must be an integer. This was the Chern number, like, this was the Chern number that we introduced earlier. And it depends on the topology of the underlying manifold. And here you have T phi square as the underlying manifold. And again, like this C must be an integer. So this kind of relates the Hall conductance to a topological invariant again. In the earlier case, I think we were, well, I mean, all we have done, like what is different from before, let me see. Yeah, I mean, we didn't use any like physical argument here. This was almost all math. Like we had this linear response formula, and it had exactly the form of a Berry curvature. And when we averaged over all possible fluxes, which are again like these external parameters that we imposed on the problem, it turned out that we got an integer which multiplied with e square over h bar. So there was no like electrons flowing from inner to outer edge, stuff like that. So this was a completely topological argument for quantization of the Hall conductance. So I think with that, I'll stop. That's all I have to discuss. Let's see, there's a question. Okay, no questions. Okay. Right. Okay, yeah, I mean, thank you for your attention. And if you have any questions, you can direct them to me now, or any comments, whatever. So, right, I mean, yeah, you could, okay. Okay, I'll take the first question first. Can Berry potential have a monopole? Exactly, so like, that's another situation. Like if you have a spin in an external magnetic field, it ends up like behaving as a magnetic monopole. And that's a different kind of situation. Let me see. I mean, at the end of the day here, the Berry phase that we get, or the Chern number that we get from just averaging over the entire surface, it's kind of telling you that there's some sort of monopole or some charge sitting inside. I think generally you can always interpret this integral of the curvature as some sort of flux due to a monopole. So in that sense, I guess you could say that there's a monopole inside this toroid, inside this torus. But I don't know if that's what you're asking. Does that answer your question? Okay, I'm assuming hints a lot to what I was saying. Okay, I mean, to probably elaborate on the monopole part. So if you take a spin, and if your Hamiltonian is like B dot S kind of Hamiltonian, where S is the spin of the electron. So there's some minus mu or something, whatever. So if B is your external parameter, in this problem, if you calculate Berry phase, it turns out that you can interpret it directly as a monopole sitting inside, sitting at B equals 0 in the parameter space. So it's sort of an abstract monopole. It's not a real monopole, like a real monopole emitting magnetic field, but it's just, so yeah, you can do that calculation on your own. Okay, what is the adiabatic approximation breaks down? Sure, yeah, I mean, so what happens is like generally when measurements are done, they're usually done in the regime where things are slowly changed. So the electric field is small. If you remember this discussion that we had in the end, where I said this, right? E equals minus del T A, and this electric field was generated by inserting some flux slowly. So when you insert that flux slowly, your electric field is also small. So if your measurements are done at small electric field, like weak electric field limits, you are basically allowed to use adiabatic expansion, adiabatic theorem, right? So that's kind of how it's justified in this last case. But of course, yeah, I mean, it doesn't always apply, and you need to be careful when you're applying the adiabatic theorem. Yeah, I hope that answers the question. Okay, I should probably just list the references for more details because I only like skimmed through the broad strokes. So my main reference for this was David Tong's excellent set of notes called Quantum Hall Effect. Chapters 1 and 2. These chapters discuss the integer quantum Hall effect. Of course, these notes are like way more detailed, and there's a lot more covered in the later chapters. There are like 4 more chapters. Okay, let me type the reference in the chat then. Okay. So David Tong, Quantum Hall Effect. There's another book by Garvin and Yan. Also, oh, okay. Did I write it in the private? Okay, sorry. David Tong, Quantum Hall Effect. So these are my main references. Yeah, so if you want more details, you can take a look at these. I also wrote a set of set of notes while preparing for this talk. I can share that with you guys if you want. Yeah, it has some more details than what I was able to cover in the talk. Okay. Yeah, I'll just send it to the MnP people. Anyone from the club, just like maybe write me a message or a mail or something. I'll send it to you. Okay. Yeah, I hope that I was able to convince you guys about all the interesting, like subtle aspects of quantum Hall effect, such as gauge invariance. And although I wasn't able to like fully explain them, but I was probably able to like excite you enough that you'd be able to learn these on your own. And I hope you got the main messages here, which was that quantization of the Hall conductance has very, very deep connections to like other areas of math and physics. So yeah, if you have got that main message, I will consider myself successful. Yeah, does anyone have any other questions? Intuition between connection between quantum Hall effect and topology. Right. Let me see. Well, intuitively, I guess what all I can tell you is that so I didn't talk about the band version or the solid state version of quantum Hall effect. All of this was like in a continuum. There was no lattice anywhere. So what I know is like when you consider a solid state system, you'll have some reciprocal space lattice. You'll have reciprocal momenta, kx and ky, and so you have this space of k vectors on which everything is defined. Your wave functions, your band structure, everything is defined on this space. And this space might have interesting topology. Like this space might be a torus. Your band might have interesting topology. Like so the let's see. Think of a vector defined on some non-trivial manifold. The vector might have interesting properties as you go around the manifold, transporting it parallelly, transporting the vector parallelly. This is where differential geometry actually comes in. So these vector fields on non-trivial manifolds are described by what are known as fiber bundles. And this fiber bundle has almost always has interesting topological features. So when you define a current operator, let's say on this K space, that current operator on the K space is described as a fiber bundle. And this fiber bundle is like a mathematical construct from algebraic topology. So that's where I guess like that's one intuitive way of seeing why topology definitely has to enter here, because we're talking about this vector operator current and we're calculating its matrix elements. So if you have a solid state system, you would be considering matrix elements between different K states. And yeah, so if you have a current operator defined, a vector field defined in a manifold, you're definitely gonna have to consider some topology. I mean, that's the only intuitive explanation I can tell you. There's a nice paper by Mahito Komoto, 1985, I think. That paper like was, I think, one of the first to actually talk in detail about this aspect. So if anyone's interested in the differential geometric and the topological aspects of this in the solid state context, you can take a look at that. But what happens is, even in a solid state system, you end up getting something very similar to this. You end up getting a Berry curvature defined on K space, and that's related in a similar way to the Hall conductance. So yeah, that was a long-winded way of answering the question, but I hope I was able to convey some information. Okay, you're welcome. Other questions? Okay, I guess there are no other questions. So yeah, I mean, thank you for tuning in, and sorry for going over time so much. And yeah, if you have any questions later, just feel free to write to me. I'm gonna share my email here on the chat, and I'll send my notes to you guys. Just like let me know who I should send it to from the MnP club. Okay, guys. If that's all, I'm gonna sign off now.